This is for the electrical power PE exam. This is an example problem from the NCEES practice exam number 513. The problem reads, for a three-phase fault at location A, the 12 kV short circuit current is most nearly location A is shown as that bus in the problem. The line impedance is given as Z equals J 0.145 per 1,000 feet. So the first thing that I did was calculate the total impedance for the line. That will end up being J 0.145 divided by 1,000 multiplied by 5280 feet per every 1 mile, and then multiply that by the 20 miles that's given in the example, and that will give you 15.3 J. So I'm going to write it up here. Z line is equal to 15.3 J. And I'll erase this. Okay, the next thing I did was select the base power and the voltage base. I selected the base power of 7.5 MVA because that's shown as the total power at the transformer. So I set that equal to S, and that is three-phase. And then for my base voltage, I just used the secondary voltage of the transformer, 12 kV. The solution in the book, they used a three-phase base power of 100 MVA. Either way, you'll get the same answer. So this will give you some different methodology and show you can get the answer both ways. So after I selected those, I calculated the base current. So I base is equal to S divided by the square root of 3 times V. And this is a three-phase base, and for the three-phase base you use the three-phase power and the line-to-line voltage, which is the 12 kV they give you in the problem. That is equal to 7.5 times 10 to the 6 divided by the square root of 3 times 12 times 10 to the 3, and that gives you 360.8 amps. I'm gonna write that up here. IB is equal to 360, we'll just say 361 amps. Okay, let's see. Let me erase this real quick. Okay, after that step, I then need to convert the line impedance that we calculated earlier. I need to calculate that on a per unit basis, and in order to do that, I used the equation from the Granger Power System Analysis book, page 29. It shows that the per unit impedance per unit Z is equal to the actual impedance, Z actual, multiplied by the base kVA divided by the base voltage squared by base V squared. So to calculate that, you just plug in the numbers. 15.3 J times 7.5 times 10 to the 6 oh, this should be MVA. No, just volt amps. It should just be volt amps. And this should just be voltage. Okay. 7.5 times 10 to the 6 volt amps. Sorry about that. Okay, and then divided by the base voltage, which is 12 times 10 to the 3 and squared. And that is going to give us a value of 0.797 J. J. Okay, so I'm going to write that up here. ZL per unit is equal to 0.797 J. Sorry, that's so messy. Erase this. Okay, next, you're already given the per unit impedance for the transformer, so Z, ZT per unit, of course, is 0.075 J, because it says it's an inductive impedance. So then you can calculate the total impedance, Z total, by just adding the 0.797 J plus the 0.075 J, and that gives you 0.872 J. So we have the base current, we have the total per unit impedance per unit. Now we can, the way that I worked this out, I'll leave the Z total there. The way that I worked it out was I just kind of drew a Thevenin diagram for it, and we also need to calculate quickly the pre-fault voltage, which is a simple calculation. It's just going to be per unit the pre-fault voltage is just going to be 12 kV, the base voltage divided by the actual voltage, which is also 12 kV, so it's just 12 divided by 12, which equals 1.0 per unit. And then the rest of the circuit is going to be the Z total, and then just the open point with a switch representing the fault location A. And this is your 0.72 J Z total. And with these two values, we can calculate the I fault per unit value. So that's just going to be I fault, and per unit is going to be 1 divided by 0.872 J, and that is going to equal negative 1.147 J, And finally, we can use all the values that we calculated in order to solve for the short circuit current. So all we're going to do for that is take our IF per unit current, and also remember that I per unit is equal to I actual divided by I base. Here, I'll write it up here. This is also an equation out of the Granger textbook. So I per unit is equal to I actual divided by I base. So to calculate the actual short circuit current, then we just multiply the base current we calculated earlier by the per unit current that we just calculated, and you'll get a final value, I actual or I short circuit, of negative J 414. And you can see that this is closest to answer choice A, which is 415 amps.